Hello everyone. Today we're going to find the response of a circuit into a periodic signal that is connected to it. As an example, you can see here VG, the source connected to this circuit, has this waveform. It's a periodic waveform, and we discussed that any periodic signal can be turned into a combination of sines and cosine, and this is called the Fourier series representation of this periodic signal. Now, how you calculate this representation is something that we're not going to put emphasis on. So we assume that this is already given to us. Now, what we want to do is to analyze this circuit and find the response using this kind of a signal. So the process went like this. We already know how to calculate the response of any circuit or analyze a circuit when the input is sinusoidal. So now this specific signal happens to be a combination of several sinusoidal signals. So what we can do is to use the superposition rule, which basically gives you the option to calculate the response of the circuit into each individual sinusoidal signal, and then once you find the responses to each individual signal, you can then add them up, and the output to the combination of these inputs would be the combination of the outputs that you have calculated. So the process is relatively simple. Now, specifically in this example, the question asked is that what is the average power that is delivered to this resistor? Now, that question may sound different, but in reality what we're really doing is to calculate the voltage across this resistor, and then once you know the voltage, then you can basically use the rule for the power calculation to calculate the power from the equation that says voltage to the power of 2 divided by the resistance is the power. Now, since the voltage is a periodic voltage, then the average power is basically the RMS voltage of the resistor to the power of 2 divided by the resistance itself, because when you have a periodic voltage, then your power is also going to be periodic. Okay, so let's start and find the voltage here in response to what we know now. We're going to do is to response of the circuit, or output of the circuit, to a sinusoidal input. Now, one of the ways that we know how to do that now is to basically find the transfer function from this voltage here to this input, and then go from there. So let's do that. Let's label the circuit and assume that this is my ground, and therefore this immediately becomes VG, writing everything in S domain already because we're looking for the transfer function. I'm going to call this V out. Now we can do this like always, label the current cell as well, and then move on to write the equations for components and KCL. So KCL, let's start with KCL. For the KCL, we have the current I1 going into node V out, and the two currents I2 and I3 leaving. Then for equations of the components, we have three components for which we haven't written the equation for. This one is already taken care of by putting VG over there. So I1 for the inductor is equal to VG minus V out divided by ls. I'm just going to use general parameters for now, and then once we calculate the transfer function, go back and replace these values. I2 is equal to v out minus 0 divided by 1 over cs, which is basically cs v out. Then finally for the resistor I3, we have v out minus 0 divided by r. Now if you take all these four equations and manipulate them so that you can get v out over vi, and keep in mind this is not complicated, you can actually use each one of these, put them v out actually over vg, put them back into this equation kcl, and then all you're left with is an equation that only includes vg and v out. So it's one step process. But I'm gonna tell you that also you could have done this without writing these equations, by just knowing that v out over vg, which is the function you're looking for, is basically just a voltage divider equation between the impedance equivalence of these two capacitor and resistors in parallel to each other over the same impedance plus the impedance of an inductor. So let's just rewrite that, and it's going to be the same thing once you do it here. So it would be the resistor in parallel with 1 over cs over the same thing, the resistor in parallel with 1 over cs plus ls. Now if you do all that calculation, the result is going to look like this: 1 over lc divided by s2 plus 1 over rcs plus 1 over lc. Now if you put the values in there, this is the function that you're going to end up getting. It's equal to 10 to the 6 divided by S2 plus 1000 square root of 2 S plus 10 to the 6. So this is our HS. Okay, now once we have the transfer function, we can actually apply any signal to this input sinusoidal signal, and then using the transfer function calculate the amplitude and phase of the output in response to that input. In other words, the output amplitude would be the input amplitude multiplied by the magnitude of this transfer function, and the phase of the output would be the phase of input plus the phase of this transfer function. Now for the calculation of the power, all I need is basically just the amplitude of the output. So I'm going to take these amplitudes that I know from these Fourier series for each different harmonic in the series, calculate the magnitude of HS for each one of them, and then multiply the input magnitude by the magnitude of the transfer function and calculate the output amplitude. Now as you can see here, this function actually ended up having a DC component, which is one of the amplitudes that you can calculate. And even for that DC component, the same thing is true. You can calculate the value of this function and multiply it by that DC, and it would give you the DC value of the output, because this is developed generally. And then for the periodic components, you have cosines, and only you have the cosines with odd harmonics. Basically you have omega t, 3 omega t, and 5 omega t. So now one thing that we haven't calculated yet is the frequency or the angular frequency of this function. As you can see, the period of this signal is 4 pi, and we know the frequency is equal to 1 over the period, or in other words, the omega, I'm going to call it omega 0, f0, is equal to 2 pi over the period. Omega is 2 pi times frequency. So putting that here, 2 pi over, now this is in milliseconds, so it would be 4 pi times 10 to the minus 3. So that would be 4 pi times 10 to the 3, which is basically 500. So omega 0 is 500, and the third harmonic is 1500, and so on and so forth. Now, we can only calculate the magnitude of the output for the first 3 elements, which is the DC component, the first harmonic, which is 500T, and then the third harmonic, which is 1500T, and that would be a pretty good approximation for what you're going to get in the output. So let's start. So for omega equal to 0, which is what we're going to calculate for the DC component, the magnitude H0, magnitude of H0 is equal to, now you put the value here. Now let's actually write this in terms of j omega. So that would be 10 to the 6 over 10 to the 6, and j omega to the power of 2 is minus omega 2, so minus omega 2 plus 1000 square root of 2 omega j. Now if you want to calculate the magnitude of, so this would be, let's actually go back. This is hj omega. Do not confuse it. Let's just quickly remove this. So, and what we have here, h j omega would be 10 to the power of 6 divided by 10 to the power of 6 minus omega to the power of 2 plus 1000 square root of 2 omega j. Now magnitude of h j omega would be the magnitude of the numerator, which is just 10 to the 6, divided by the magnitude of the denominator, which is basically a complex number. So it would be the square root of the real part of that complex number to the power of 2, which is 10 to the 6 minus omega 2 to the power of 2, plus the imaginary component of that complex number to the power of 2, which would be again 10 to the 6 times 2 omega. So let's actually do this. So it would be 2 times 10 to the 6 omega to the power of 2. Good. So now we go back here. So putting omega equal to 0 in this equation, this term goes away, 10 to the 6 comes out of the square root, and then you get a 1. So what that tells you is that the magnitude of the output in response to a DC component 10 would be 10 times 1, which is just 10. In other words, all of the DC component is going to pass through. And looking at this circuit is actually makes sense, because you have between the input and the output, you have an inductor, and for a DC, we know that an inductor basically could be represented with a short circuit, and given that, the input and output are going to have the same voltage. So that now makes sense. So now for omega equal to 500, which is the first harmonic, we have to do the same thing. Calculate the H of 500 J, magnitude of it. In other words, put 500 in this equation and calculate the magnitude. Once you do that, as it turns out, the value turns out to be 0.9701. So in other words, you take the first amplitude, which now you put n equal to 1 here, and you get minus 80 divided by pi over 2. Then you multiply that by 0.9701, and that would be the response to that first harmonic. Now omega equal to 1500, which is your third harmonic, and this time the magnitude of H times 1500 J. Again, you have to put that value here, and that turns out to be 0.4061. Now with these three, we're gonna stop, and as it turns out, this would be a pretty good approximation, because the next one, when you calculate the fifth harmonic, this value is going to be too small compared to these, and therefore you already know that that component is not going to have much of an effect in the output. Now, in order to calculate the power, the average power, as we said, you have to have the RMS value of this. So you have to have the out RMS, and then take that to the power of 2 and divide that by the resistance. So the RMS value of the output, this is something that you can do. So V out RMS is basically the amplitude square root of the RMS, each RMS value of each component of the output to the power of 2. So now the first component would be 10 multiplied by 1, which is 10. So that would be 10 to the power of 2. We get this. And then that plus. So the second component would be 80 divided by pi over 2 multiplied by 0.9701. And then that's the amplitude of the output. The RMS of that would be the amplitude divided by square root of 2. So you do all that. So you do basically 80 divided by pi over 2. Then square root of 2, all of that multiplied by 0.971, and that to the power of 2. So that's for the first harmonic. And then for the third harmonic, this time you have 80 divided by pi over to the power of 2 divided by 9. So 80 divided by pi, 9 pi to the power of 2, square root of 2, and this time multiplied by 0.406, 0.4061, and that to the power of 2. You calculate all of that. The value that you can calculate is it's about 11.44 volts. So now you take that, put that in this equation. So that would be 11.44 to the power of 2 divided by 50 square root of 2. And that concludes the calculation for the average power that is delivered to this resistor. Obviously, this is an approximation, and in order to get an accurate value, you have to continue doing this for all the higher harmonics. And the more harmonics that you add, the more accurate your output is going to be. But this calculation, or what the value you calculated, is going to be really close to the actual value, given that the next harmonic is going to have a really small amplitude compared to these three first ones. I hope this has been helpful. Thank you for your attention, and have a good day.